Okay, so welcome to the next lecture. Today we'll talk about, as we were discussing, we'll talk about how to understand the data sheet. We need to understand how the LED works, what are the operating characteristics, how do you differentiate one LED to another LED, what are the maximum power that it can emit, how we can use the lasers, what are the limitations of using the lasers, and how to choose a detector. There are a lot of different kinds of detectors, so we'll learn about when to use when. Okay, so let us start first with the LED, and this Broadcom is one of the manufacturer of the LED, and you can see many LEDs being developed by Broadcom. And what you see over here is this is the first sheet that you open and you download any data sheet of any LED. It will first talk about the company, and then this over here would be a part number. Okay, so then it talks about what kind of LED is it, whether it's surface mount or it is a through hole. It will give a brief introduction to the light emitting diode, the first page, okay, of the data sheet. Next, in this data sheet, it's talking about the dimensions of the LED. It seems that it is a SMD. SMD means surface mount device over here. So in the next page is talking about the dimensions of the LED. Usually this dimension of LED may be in the end of the data sheet as well. Most important of the data sheet is the ratings. So what is the maximum rating? That is how much maximum current that you can actually tune to your LED, that is light emitting diode. Okay, so here you can see that the maximum DC forward current is around 25 milliamperes. So you should not actually drive more than 25 milliamperes. And whether it is lasers or light emitting diode, as you will see that the most important thing is the current. How are you giving the current to your optoelectronic device? That is one of the most important thing that you have to make sure that you are doing it correctly. Otherwise, the voltage doesn't actually much matter unless until how much you are driving the current. So over here also you will see that in most of data sheet the current is kind of the most of the important thing that they will focus on. Okay, and then second is the power dissipation. So how much the power is going to emit and how much it's going to loss as a heat source. So those things it can also be mentioned. Now the second thing is the the optical characteristics. So that is to know what is the wavelength of your light emitting diode. That is one of the most important thing, in addition to the how much you are driving the laser with. That is, you can see over here that the dominant wavelength LD is 639 nanometers. Okay, peak wavelength, that is around 660 nanometers, and it has a viewing angle. So I will just talk about what is a viewing angle, or it also known as half width full maximum in some time. And then it talks about the electrical characteristics. So it will talk about, the data sheet will talk about optical characteristic as well as electrical characteristics. Okay, so the main thing that you have to see is the peak wavelength. Okay, that is the most lambda p, which is around 660 nanometers. So that is what is the very important. It has to overlap with the if you're talking about any clinical diagnosis, then the absorption peak of a particular tissue constituent should overlap with this peak wavelength. Okay. Okay, so voltage also is a kind of a important parameter to drive it. So here we can actually give between 1.6 to 2.6 volts. But the current has to be around 25 milliamperes maximum. That is the important part. Okay. So here you can see what is the spectral distribution. Now when we talk about spectral power distribution, it's a graph with x-axis as wavelength and y-axis as relative intensity. That is how much intensity it is giving me, the light source. So it's actually varying with respect to the wavelength. Now I don't have any green light source over here or blue light source over here. It's only purely green, purely red over here, as you can see. That is around 660 nanometers. Okay. Now the peak wavelength, as you can see, is around 660 nanometers. And the second thing is the viewing angle or the full width half maximum, that is 2 theta. double the theta, where theta is the viewing angle. Okay, so here full width half maximum, you can see it's around 660 to around 650 to around 670. So the viewing angle would be around half of that full width half maximum, around 7 to 10 or so. Okay, the next thing is the radiation pattern. So this is this is the one that I was discussing earlier. That is the full width half maximum for the bandwidth, not the viewing angle. The viewing angle is defined by the radiation pattern. So what you see over here, you see that it is starting. So again over here we have the full width half maximum, but it is related to the radiation pattern. Earlier we talked about FWHM, that is full width half maximum with respect to the spectral distribution. Now we talk about with respect to the radiation pattern. With radiation pattern, the half of it, that is from 0 to 70, 75 degrees Celsius degrees is the half angle or the view angle. Okay. Okay. So the next thing that you see in the data sheet is that is the graph that if you increase the forward current, how much is the intensity going to increase. That is one of the most important graph, that is to understand how much is the light source that you want, right. So for example, if I am operating with around 10 milliamperes, I am going to get around 0.6 normalized luminous intensity. If I now drive my LED with around 20 milliamperes, I am going to get almost the double, around 1 normalized luminous intensity, right. Similarly, if I go to around 30 milliampere, I get around 1.2 1.4 times the normalized luminous intensity, right. So similar to this, you can also see the graph from forward voltage versus forward current over here, right. So these are the main characteristics that you need to see from the data sheet. A data sheet would be like 20-30 pages sometime, so you might get kind of very much overwhelmed, but these are the main things that you need to see before selecting a light emitting diode for any of the optical systems. Okay. Now you want to drive your light emitting diode. So how do you drive that light emitting diode? One of the simplest way is to use LM317. It is a voltage constant driver. You can use it to make it as a constant current driver as well. Okay. So if you use a particular resistance over here, you can actually make sure that the current that is through the LED is so it's actually a function of the resistance. So if I am able to write over here, can I write it? Let me just check it. Yeah, so if this my resistance is around R over here, so the current that is going through my LED is going to be almost to be 1.25 divided by R. So this is how the circuit is kind of built, and this LM317 is kind of built with. You will always get this current when you put the resistor. For example, your resistance is around 100 ohms, so you will get around 1.25 divided by 100. So it's around how much you get it, around 1.25 divided by 100 will get 0.00125. So you will get around 1.25 or around 12 milliamperes. You can just calculate it out, and that's how you will get. Okay. Okay, fine. Okay, that's good. So now let us move ahead with the laser. Again, this is a laser developed or fabricated by OSRAM, and this is the first page of the data sheet, and it always mentions the part number. So part number is kind of very important thing that you have to check once you are buying a laser or a light emitting diode or a detector. It talks about few of the features and the application, and then it talks about perhaps how the casing of this laser. Okay. It will also talk about which is very important is the wavelength. what is the typical wavelength. So that is mentioned in the first page because it's kind of a very important part when you're buying any optoelectronic components. So over here it's mentioned that it's total emitting wavelength is around 450 nanometers. Okay, that's good. So now the next thing again we talk about is the maximum rating, that is how much is the maximum that you can drive the laser with. So the peak output wavelength, the peak output power is around 120 milliwatts. Okay, that is the maximum power that the laser can actually give, and the forward current is around 165 milliampere. That's very significant. As you see, earlier we were driving the LED, we were choosing only around 10 to 20 milliamperes, but to drive the laser we are giving around 165 milliamperes. It's kind of almost 10 times the current that is required for the light emitting diode. So, but even the laser is like more output power also is kind of similar, significant as compared to the light emitting diodes. Okay. Now other things are the characteristics, that is the electrical characteristic as well as the optical characteristics. So both the characteristics we actually see. So here you can see that we have operating current. So typically we need to operate around 75 milliamperes, right. So maximum is given as 145 milliamperes. So we should not actually operate more than that. Okay. We have operating voltage, so maximum kind of 5.4 volts, typical around 5.2 volts, maximum 6.5 volts, and then talk about the peak wavelength, which is around 450 nanometers, that is the blue light. And then the spectral bandwidth, that is the delta f or delta lambda, and then we talk about the viewing angle as well. Okay. So here is the spectral distribution, that is the at what wavelength will the laser emit. And what interesting thing, you can see that the emission wavelength actually changes with respect to the temperature. So this is around 25 degrees Celsius, that is at the room temperature, and then after some time when it becomes very hot, you will see that it actually shifts. So at normal room temperature it is giving a light of around 450 nanometers, but at the 60 degrees Celsius it gives a light of having a peak around 452 nanometers, right. So it's kind of temperature dependent wavelength, right. And at the same time we can see that the beam divergence is not completely like cylindrical, but it's kind of has its own axis, that is parallel as well as the perpendicular axis. So you can see that the laser is not emitting a perfect circular light source which is kind of cylindrical, which is kind of moving from this to this place, but it's kind of a cylindrical light source like this, which is kind of moving forward. Okay. And that's why with the beam divergence you can see that is theta parallel as well as theta perpendicular, both the ellipse minor and major axis, it's giving about both the degrees of viewing angle. Okay. Another thing which is important is the how much are you going to drive the current, that is you can see that you are driving around 40, then you get around 30 milliwatt. If you are driving around 60 milliamperes, you are getting around 60 milliwatts, and so on and so forth. So as you go on increasing the current, the power which is going to be the output of that laser is going to also linearly increasing in this case. Okay, and this is the relatively safe regime with which you can actually work with. Okay, so as we discussed earlier, for the light emitting diode we also have a curve with current versus the voltage graph, right. And one more important point that especially comes with the laser is what is the maximum permissible exposure level, so which is also known as MPE levels. So this graph talks about for different wavelengths. So this graph, first the green curve talks about for the lasers operating in the visible spectrum, and on the x-axis is the exposure time, that is we can use either a pulse source over here and we can use a continuous light source for a long period of time, and what is on the y-axis is the maximum permissible exposure, in the units is watt per centimeter square, that is the light you are shining it on how much surface, right. So just a ratio of power that you discussed some time back with the ratio of, with the denominator as the area with which you are shining the light on. So, smaller the area, higher is the MPE. Larger the area that you are shining the laser light, smaller is the MPE, right. So, or exposure levels. Okay. So, here this is for the 800, that is NIR, then you go for infrared, and then you have the ultraviolet. So, the 266 nanometer is kind of an UV light source, 355 even in the UV light source, and then this is the near infrared to mid infrared regime over here. Okay. So, usually you will see that the dimensions of the lasers, the side view, front view, everything would be given in the end of the data sheet. Okay, as you can see over here, and this is basically required if you want to make any optical systems. Then in those cases you will require the dimensions to build one particular probe or a tool or a system. Okay. Now, to drive the laser, again you need to make use of a constant driver circuit. One of the ways is to use LM317. That's what most of the people use it. It's a very simple driving circuit, but if you want to make a more suitable driving circuit, then there are other ways to do that as well. Okay. Okay. So, now coming to the last part of the discussion of the data sheets of different optoelectronic component is the photodetector. A photodetector is a component with which you can detect a particular light source. The most important part of the photodetector is the material that is being used in the photodetector. Now, in the photodetector, what happens is that different materials can absorb lights of different range of wavelengths. So, in this case, you can see over here, this photodetector works specifically between 750 nanometers and 1100 or 1100 nanometers. So, it is only between this regime from 750 nanometers to 1100 nanometers can it actually absorb the light source. And it is not a kind of a constant absorption between 750 to 1100, but it would be some kind of a Gaussian relationship between 750 to 1100. It also have its part number, again kind of very important. So, if you read any papers, it is very important to see if there are any part number given, so that you can easily make the bill of material by the photodetectors or the LED lasers or LEDs. Okay. So, then it talks about the maximum rating as we were discussing earlier. So, what is the maximum temperature, what is the maximum voltage that it can be given across it, right. And then talk about the characteristics, electrical as well as the optical characteristics. So, you can see it has the wavelength of maximum intensity, sensitivity. So, as I said, it is kind of a Gaussian curve that you will see in some time. So, its maximum intensity is around 900 nanometers, right. Now, this detector also has its own angle. It cannot receive from all the angles, it will receive only for a particular angle. So, that is the viewing angle, right. And then it has dark current, that is if it is not working, then it still be actually means even though there is no light source, it will still be giving some current through this photodetector, that is in terms of nano amperes, that is kind of very less. Then you have the forward voltage, and then you have the rise time and fall time. So, a lot of components, a lot of characteristic electrical as well as optical would be mentioned in the data sheet. Over here, as I was saying, that it's having a full width half maximum at around 750 nanometers, and then dying down around 1100 nanometers. You can see over here. This is a relative spectral sensitivity. Okay. So, for lasers and LEDs, we have spectral distribution, but in this case, we have a spectral sensitivity because it has to sense as a function of wavelength. Okay. So, here this is the spectral sensitivity, and you can also make it full width half maximum to understand what is the bandwidth. And on the right hand side, it's the directional characteristic. So, if you've seen lasers and LEDs, we talk about radiation characteristic, radiation pattern, but in this case is a directional characteristic, that is eventually you get to understand what is the viewing angle from this graph as well. Okay, then it talks about the dimensional drawing. So in the end of the data sheet, it will also talk about the dimension of how it is going to dimension of for making a particular optical system or a probe. To drive this photodetector, photodiode, there could be two modes. Either you can go for photovoltaic mode, or second is the photoconductive mode. So both has its own applications. If you are interested, you can go through few of these references to learn about how to drive the photodiode. So most of the times using op-amps is one of the best way to drive the photodiodes, because it's kind of more sensitive, and you can easily use another photodiode for amplification purpose as well. Okay, so thanks a lot for your attention. Today we talked about light emitting diodes, lasers as well as photodetector, how to understand the key parameters from each of the data sheet of each of the components, and how to make tools by understanding the dimensional drawing of each of the components. Thank you.
Recording